All right, everybody, let's keep on rolling. So Patrick Arlt is an applications engineer at ESRI, which if you don't know, he was previously at Geoloki, but they're world experts in mapping. And so, as we may expect, he's going to talk to us about mapping, but he's going to tell us everything we never wanted to know about maps, which I kind of love maps, so that's a bit of a challenge. There's not very much that I did not want to know, but I'm excited to see what he's got for us. So everyone give a hand to Patrick.
Hey everyone, I'm Patrick Arlt. You can follow me on Twitter. I just tweeted a link to the slides. It looks like the monitors just sort of cut up the bit.ly link, which is fine. And it's really awesome that I went like immediately after Willow, because now it's a lot easier to explain what ESRI does, because I feel like we try to do everything, and when you have really specific examples to hone in on, it actually gets really easy to explain. See, I immediately regretted that. So what we actually do is we actually do a lot of visualization and analysis of spatial data, and a lot of our customers are kind of in that government, utility, natural disaster response kind of area. So a lot of the things that you would do with our software is plan where to put the new fire station so that it's accessible to the largest percentage of the population that isn't covered by an existing fire station, or based on the population data, where do you put the aid center so that it's accessible to the most number of people within a 10-minute walk, and doing those kinds of things. We even do things like real-time analysis of Twitter data so that you can hopefully try to consume some of that stuff and actually run analysis against it to see where people are tweeting the most about fire or water or that they need food. So a lot of that kind of stuff is things that we do. I'm going to see if that's very interesting. So, and working at ESRI, I've been there for about 2 years, and before that, I was at Geoloki for about a year and a half. And at Geoloki, I made a lot of maps. I made very simple maps. They were, some map tiles with a pin and a pop-up, and you would configure something, and then that was it. And then I got to ESRI, and I was kind of exposed. There's this whole other world of map making that's so much more than just putting a dot on a map. And it was really exciting, but at the same time, there's a whole profession and a whole education system and a whole structure built around making really authoritative, accurate, perfect maps. And it was really interesting learning about how our customers like to make maps, because our customers aren't people like us. They're people who work in the Forest Service, or they work for the Red Cross, and they have a 4-year degree in working with spatial data, and oftentimes they have a specific certification for working with our software. So the maps that they're making tend to focus on being very authoritative. They are publishing the data as an authority on the data. The Forest Service tells you that the forest ends at this inch, not at this meter or at this mile. It's really very accurate. And it also means that they work in these huge enterprises with tons and tons of other people doing the exact same thing. They have planes that fly over forests. They have dozens of people out in the field. They have hundreds of analysts working on desktops. And when they make applications, all the applications that they make are really centered around maps. The map becomes the centerpiece of the application, whereas with what I was doing, the map was just a little part of the application, and there was a whole bunch of other stuff. So what I work on is I work at the PDX R&D Center for ESRI, is I actually try to bridge that gap and bring people doing GIS and actual software developers together. And this was never more apparent to me than immediately after Geoloki got acquired by ESRI, we went down to Redlands, and we were there for 2 weeks, and I was trying to convert all of the maps that I'd written previously to use ESRI's tools. And there was this massive terminology gap. I couldn't talk to anyone at the company about anything because I was using all the wrong words. And I was like, yeah, so how do I make a bounding box? And they're like, what's a bounding box? And I was like, this is crazy, because their word is completely different than the word I'm using. So there's actually a slide somewhere in a slide in a PowerPoint that is just a giant list of ESRI term, our term. And I tried to find it for this talk and couldn't, but it's fine. But that really formed the basis for not quite everything you never wanted to know about maps.
Yeah, that's good.
And it's really this concept of there's this whole other world that we as software developers don't really know about unless we're working with maps and spatial data all the time. And some of the concepts are really exciting, and if you know them, you can manipulate them to make better applications. So one of the things that really kind of struck me at first is we're all used to looking at like the Google Maps version of the world or the Mapbox version of the world, and it's a perfect square, and the US looks about the same size as Africa, and really that's like a total and complete lie, right? So there's this whole field of map projection, and it's all very mathematical, and it makes me wish I did more geometry in college and didn't do Italian, but that's a regret. So how do you flatten the Earth and show it in 2 dimensions? Like, the Earth is a sphere. It would be a lot easier if it wasn't, but that's what we were given that. So you have these different kinds of surfaces that you can actually unwrap the Earth around. You can put a plane and actually project the Earth onto that planar surface. You can project the Earth into a cylinder and then unwrap the cylinder to be a flat object. You can do the same thing with a cone. And then depending on how you do that projection onto your surface, you can actually preserve different aspects. You can preserve areas of continents. You can preserve certain lines. You can preserve the distances between certain points. So special thanks to like people who work on D3 geoprojection, because I actually just copied all these examples from them. So I was like, oh man, I'm going to have to actually learn how to do this. And it was actually just like copy and pasting their code. So I want to talk about like some of those different projections though, because they're really interesting when you look at them. And the first one is actually the azimuthal projections, which actually project the globe onto a plane. And these are really interesting because they orient everything around the center point. So in this case, the center point is kind of, maybe it's like just off of New York, like right there. And everything, all the distances to and from that center point are actually preserved. So everything kind of radiates out around that center point, which kind of lies in contrast to the map that most of us are used to looking at, which is a cylindrical one. Right? This isn't working. Oh well. So project the Earth into a cylinder and then unwrap the cylinder, and then you end up with something that looks mostly like the world map that most of us know. So those are the most familiar ones. And then there's also some fun ones like cones, right? Put the tip of the cone at the North Pole, and then everything else radiates around from that, and then you can just unwrap the cone and it looks like that, which is totally useful, right? Except it gets a lot more useful if you're looking at like just Russia, which is very northern, so it's actually not, it's going to look a little different. You're not going to look at Antarctica like this, but it's really useful to look at, North America, the Arctic Circle, and things like that. So then getting into kind of the preservation of properties of some of these projections, you have things like stereographic projections, which preserve all of the angles. And if you can see, the projections, it's centered right around the North Pole, and all of the lines radiate out from that are actually perfectly preserved. Those are all the latitude and longitude lines, and they're all perfect. So it's actually preserved all the angles around the North Pole for us. And then you can move into other projections like Mercator projections. And Mercator projections were, they're really old, and they were all designed for navigation, but this is what most of us are used to looking at. We're actually used to looking at this map that was designed for navigation 400 years ago, and we don't even know it. And it's basically that way because it preserves all the lines as straight lines. So when you would navigate, instead of plotting your navigation as a curve, you would just plot it along one of these lines, and it would be straight. So you're like, yes, go west. Okay, we're going west. That's great. Like, it works. And that made a lot of people very angry because it made all the European and North American countries seem really big. So someone got very mad about that, and they made equal area maps, which preserve the ratios of all the countries to each other. So this isn't stretched or distorted or anything. This is actually how the map looks. It's not a mistake. And that Africa is actually that big compared to the US. Like, this is not a lie. And if you go on YouTube and Google for like equal area map White House, you get a really amazing clip from the West Wing. Where they're arguing about like trying to make this the standard projection in American schools because it shows things in their proper proportion, and it's kind of entertaining, and the socioeconomic repercussions of showing Africa this big. And then there's some other ones. You have equidistant projections, which are really good at showing distance along a line. So all the distances between all the meridians are preserved. So the map ends up appearing wider. It's really good for widescreen displays. And then you have my personal favorite, which is Dymaxion projections, which actually turn the Earth into a 20-sided triangle and then unwraps the whole thing. And it's like, yeah, this is perfect. Like, this is totally obvious to everyone what this is. But what's interesting is if you look at how this distorts the Earth, it really doesn't distort it all that much. It's like almost perfect. So this is really like one of the best. And if you want to have some fun, I highly recommend, I'm actually going to see if I can play this a little bit. Google did a really funny demo called the Google Mercator puzzle, where you can actually look at how shapes get distorted as they move around the globe. So this is Mexico, and we know it's Mexico, but if you put Mexico up by like where Greenland is, it doesn't really look like Mexico anymore. And you can actually play the game and try to figure out where the countries go, which is funny. Oh, sad. Where'd that go? It's completely disappeared. No, it's not on my other screen. I'm just going to have to go back to mirroring. This isn't going to work. All right. It still isn't on my screen. That's awesome. Just like completely disappeared. Right, we've done all that. That's fine. Map projections. Yeah, good. Mercator. Right. So projections, I did them first, even though this was like the really confusing concept when I first got to ESRI, is spatial reference systems. Like the first thing I did was I was like, okay, I'm going to like center the map on a point. Right? Like that's the first thing I want to do. I want to like center the map on Portland. And at the time, you couldn't actually center the map on a point in our API. You had to center it on a bounding box. And I was like, okay, well, I'm going to just make a bounding box. And then I made a bounding box that was like, okay, this latitude and longitude and this other latitude and longitude, now make a map out of it. And it didn't work. And I was like, this is really bizarre. And they're like, oh, well, you have to project the data. And this is really obvious to someone who has a 4-year degree in geography, but I have a 4-year degree in art. And I didn't pass Math 90, so I didn't really know. And eventually, I learned what all this meant. And it's really important because if I ask you a question like, where is 45, 52, 17 minus 21, 64, 47, like, you don't know where that is. Unless Aaron Parecki is in the audience. But, like, you don't know where that is. You don't know where 0 is. You don't know, like, if that's in degrees or meters or seconds or miles or nautical miles. Right, but if I show you something like this, a GIS person can look at this and be like, oh yes, I know exactly where that point is. It's our office downtown. And this is actually really interesting. This is a standard for defining spatial reference systems. So they're actually defining the models and the mathematical models of the globe that you can actually plot points on. So I know where 47, 52, 17 minus 122 is because I know that we're using this particular model for representing a sphere of the Earth, and we're using this particular degree unit, and we're using, well, you're using Greenwich as a prime meridian, so that's where 0 is. And I know all those things, and now I can actually plot that point on the globe. So that's actually a geographic coordinate system. It's just latitude and longitude onto a spherical model of the Earth, and it defines a couple things, like what unit of measurement you're using. Are you using degrees? Are you using like arc minutes or arc seconds or decimal degrees? Where is the prime meridian? The prime meridian could be in Portland for all we care. It could be along the date line. Most of them, thankfully, keep it in Greenwich, so it's actually good. Which spherical model of the Earth are you using? The Earth isn't like totally perfectly a sphere. It's kind of lumpy and squishes out toward the equator a little bit. So there's actually been surveying done against the surface of the Earth to build these models so that we can actually like map things onto the surface of the Earth down to like really precise accuracy. And then finally we have control points, like predefined points that we know where this point is, so we know where this has to be. And we can use all these things, or rather I can't, but software can, because software is amazing, to actually figure out where this stuff is. So this is EPSG 4326, which is totally obvious also if you have a 4-year degree in geography, right? EPSG, I just found this out the other day. I had to look it up. It's the European Petroleum something group, scientific group. And they actually do a lot of work defining all of these things. Like this is the worldwide one, and this is this other one, and they actually are probably the main authority on this. But this one's cool because this is what GPS uses in your phone. So when you get latitude and longitude from your phone, this is actually what it's doing to figure out where you are based on what the satellites are telling it. So, and then you actually go one level deeper. So now we know where a point is in 3D on the Earth, and we still can't draw it because we're drawing on a 2D surface, right? Web browsers are in 2D. It doesn't really work. Like, we have WebGL now, but you don't want to do that. So you actually need to project that point and figure out where it sits on the globe. So you plot it into a point of x and y. And that's usually, meters, pixels, feet, inches, whatever. And then this also tripped me up. This, still to this very day, I've worked with maps for 4 years. X equals longitude, y equals latitude. They get flipped. Remember that. It will save you a whole day of your life someday when you have to do this. So this is another projection, except this one is actually a projected reference. So this is EPSG 8557, more magical numbers that just mean things, right? But it's actually interesting because you can actually just read through this and kind of figure out what it means, right? We have a projected coordinate reference system called pseudo-Mercator. It contains this other geographic model of the Earth that I just showed you. And then it defines a bunch of other properties like, this is the central meridian is at 0. The unit is meters. The x-axis manages east to west. The y-axis manages north to south. So this is actually Web Mercator. This is the default, in Google Maps and Leaflet. It's actually the default in our own APIs too. So this is really nice because it just makes a very easy to represent spherical model of the globe. The globe is square, so when you make map tiles, you've got one tile that represents the Earth, and then you subdivide that into 4 tiles, and then that's where you get those zoom levels that go down the Earth. So I'm going to give you a little demo. This is actually how this works inside of Leaflet, which is my personal favorite open source mapping library. They actually have a whole set of these coordinate reference system objects, and they have methods on them like, turn this latitude and longitude into a point I can draw on the map, please. And this is really great because all it does is you give it a latitude and longitude and you give it what zoom level you're looking at, and it just goes, great, I'm going to project this latitude and longitude into meters, and then I'm going to scale those meters to a particular zoom level so you're not drawing a point at minus 6,000 meters. You're just drawing it at minus 500 pixels. And then this just returns the x and y you should draw that point at, which is really interesting. And it's actually, I show Leaflet because this is actually the simplest way to do it. It gets way more complicated as you kind of build out and try to support other things. But that's it. Convert the lat long into meters, and then scale the meters based on what zoom level you're looking at the map on, and now you have x and y in coordinates, and you can actually draw the point on the map. So this gets a little more complicated because when you're working with government data and stuff like that, it tends to be required to be in a particular reference system that you don't really want to work in. Most likely if you're in the US agencies are usually required to publish their data in a particular state plane, which I made this fun little demo of state planes, and you can't see the magic. Oh, there it is. So this is the US, and it's the US in a projection called Albers, which is really good at showing the US and really bad at showing the rest of the world. But if I actually switch this and I say I want to look at Oregon North State Plain, the northern part of Oregon looks really nice now. That little northern chunk of Oregon looks great. And the rest of the US looks kind of weird. It's a weird angle. We don't really have a good reference point. It doesn't look like the world. And then if you do something look at Florida West, the western part of Florida looks really good, but when you get up to what is that part of Idaho, or what's, this part of, so a lot of the data that you'll find from open data websites is actually already in these weird kinds of formats, which is a total pain in the ass. Everything should just be lat long, and it should be GeoJSON because we like JSON, and it's easy to read, right? I don't want to leave you guys with all this knowledge without some tools to let you actually do this stuff. So when you encounter data like this, you can be like, yes, I know how to work with that. It will work. So 2 of my favorites are Ogre to Ogre, which is a command line tool, and then actually Proj4JS, which implements all this math for you in JavaScript, and it is pretty amazing. So the first example I have is if you have a shapefile, and a shapefile is a format from ESRI that's semi-open. It's kind of like your docx for geodata. And it's good for passing around large blobs of geodata. You can actually use Ogre to Ogre. You just crank that up. To convert it to GeoJSON, it'll just magically work. And you just say, I want to make a new file called parks.geojson. Here's my shapefile. Output this as GeoJSON. Output this in 4326 because I want latitude and longitude. And it actually just does it. And the reason it can do that is, I'll change my screen size, don't worry. Also going to regret that later. right? So here's Portland Parks. This is actually that folder that I'm telling it to look at it, and there's a bunch of junk in there. But if I actually look at, let's see, here, J, if I actually look at this parktrails.prj, it looks exactly like the format that I was showing earlier for a coordinate system. There's projected coordinate system 1983 Harn State Plane, Oregon North. Like, this is data for Northern Oregon, so it was published in that specific reference. But then I can actually just convert that, and that demo actually comes out looking like this in GeoJSON. So I can actually see all the data, and there it is on the map. And it's all mapped very nicely for me, and it all works. So then the second demo is actually doing kind of the same thing, but with Proj4JS and JavaScript, because this is CascadiaJS, and I haven't talked about JavaScript yet. So something is clearly wrong. Go back. Right, so I have some geodata. So I have a CSV of graffiti locations from New York, and that has like X and Y. And X and Y is actually in New York, State Plane, Long Island, which is completely meaningless to me. So you can actually write a little node script to do this for you, where you can actually require Proj4JS and require the CSV parser, and then you can actually go to spatialreference.org and actually just look up, like, what is New York State Plane? And it gives you this nice little URL for, like, yes, this is New York State Plane for Proj4JS. Just paste it in. Like, it's a string that looks really weird, right? This is like more like magic numbers. You just have to know what the magic numbers mean. I should have just called this talk like magic numbers, and it would have been way better. So then you actually just like read the streaming CSV and then just like, hey, look, Proj4JS, take New York State Plane and convert it to lat long for me, please. And here is your X and Y. And it just gives you another X and Y that represents latitude and longitude for that. And that's gonna, oh, there's my speaker notes now that are now out of sync. Right, so then that actually just looks, oh, there you go. So this is actually some graffiti report data from New York City that actually was New York State Plane, and now it is GeoJSON, and I can actually do it. And you can see the original X and Y there. So that's in meters from some random reference point in New York, somewhere. Like, you don't really know where. You could look it up, but it's not entirely necessary. So I'm probably, close-ish out of time. So I want to show some kind of fun demos and some stuff that I'm seeing that's happening with maps that I think is really, really amazing. And probably one of the coolest ones that I've seen recently is actually Mapbox is doing a lot of work with, we'll close those, is doing a lot of work with WebGL and OpenStreetMap data. And they've actually got, this is actually like a live demo on the web where you can actually pan and zoom, and it's not chunky anymore. Like, there's no zoom levels. It's very fluid and smooth, and this is all WebGL powered. And this is the same stuff that the new Google Maps is using. So bringing vector data directly onto the client. No more images. Like, that's something that's definitely going to happen. It's going to be worked on because WebGL actually has the performance now, and browsers are powerful enough. You can bring that to browsers. My other favorite ones that I've been seeing is actually the OSU Cartography Lab has a pretty funky looking demo that actually dynamically changes which map projection you're using for your map. So as I zoom in, you can see the other parts of the map kind of distort. And it actually tries to select, based on this little scale down here, which part of the world I'm looking at, and dynamically alter all the data that I'm showing on the map to show me the best representation of that particular part of the world. So the same thing has also been done in D3, which is kind of interesting as well. So you can see that it kind of goes out and it's like, okay, well, we'll make the world bigger. And then if I spin it around here, you can see it's eventually going to just kind of changes a little bit, very subtly, as you kind of zoom in and out around the world. So it still is a flat map, but it actually alters whatever it's doing to kind of meet the needs of what I'm looking at currently, so it's always accurate. And then I didn't preload any of these demos, so they're going to take forever. At ESRI, we've kind of been ignoring the vector maps thing and working really, really hard on doing 3D. So we were actually doing 3D mapping, and this is all WebGL in the browser, no plugins. But in contrast to other 3D demos that you've seen from like Apple and Google, this is actually interactive. So I can click on this and be like, this is the Texas Schoolbook Repository building, and this is a real model of the crime scene from the JFK assassination with real bullet trails for this is where the first one went, this is where the second one went, this is where the third one went. You can explore the whole thing. So those are some fun demos. And then lastly, this is, this one's for Jason Denzak, who's an organizer, cat tiles. This is going to be a really big thing. Thanks to Lorem Pixel for letting me totally abuse their service to actually generate all these cats, which is really funny. So now you can have a map with, cat tiles, because that's going to totally work. This is real. It's like really geographically referenced data. I have the United States on there to prove it. It's not just like a wall of cat images. So that's it. That's all I have. Thank you.